Thank you very much. Okay, Assalamu alaikum. This is our class number 2 of week 7. We are going really step by step about the chapter number 3, sorry. And today, inshallah, we cover section number 3.7. And basically, so far, we have been talking. So we talked about the junction, then the diode, then the applications. Yes or no? Now more applications. You can see the diode is nothing but the junction, but when you apply it, it makes wonders. If you remember the video that we started this course with, remember? It's amazing. Just a diode, huh? Boom. So if you remember this, and I mentioned that to Bilal for a good question he asked, the humankind, the mankind was created by just 2 people. Man and Eve, Adam and Hawa. Look at this. Civilization, booms, positive stuff, crimes, etc., good stuff, etc., etc., lots of stuff. So here, just with PN junction, all the microelectronic industry fleshed out, okay, which is amazing. So that shows the importance of these 2 elements, the N-type and P-type. And when we put them together, the whole industry startup. Okay. Now, today, inshallah, we see a different side of the application. Now, it's not in the circuit level. So what we studied before is called circuit level. Why? Because we use diodes in the circuit and to do some function. Could be voltage regulator, yes or no? Could be rectifier, half wave, full wave. By the way, the 2 are full wave, that we studied in this quiz. Now, could be what? So this or that. Well, that's good enough too. Now more to that application. Now that was circuit level because it's in circuit. These ones they are part of the circuit and we need them alone there. They are called special diodes. Special diodes because they do special things. So the first special diode we talk here, we're not going to go deep because it's a lot of science, a lot of engineering behind it, is the Schottky barrier diode or SBD diode. So what is this diode typically? Okay. In terms of symbol, it looks like the zero diode, except it has an extra symbol here and there. If you hide these 2, these last 2, it's regular. The zero is actually a little bit different, but just adding these 2 will make a difference between a regular diode and the Schottky barrier diode. So what is it exactly? So you can see, you can go to this link, which is really, really good. There's lots of things I can teach you there about this type of diodes. Okay, it's a tutorial website about that. So basically, this diode is just a junction between what? Between a metal and semiconductor. That's it. It's a junction of metal and semiconductor. And it has special properties. When you bring the metal with the semiconductor, it brings extra properties, and this semiconductor actually has to be N because the metal by definition is P. Okay, it's like positive charge. It's not positive charge, it's a positive pole, if you will, because it may or may not be charged. Anyways, so this junction, so this Schottky barrier junction is also called or known as the Schottky, what's called? Schottky or hot carrier diode. Why a hot carrier diode? Because these carriers that are hot, I'm not going to go deep, hot in terms of speed, because we know that if we heat we heat the atoms, they vibrate more. Same thing, if you heat also the electron, give them energy, like heat energy, they go really fast. And if you remember, Boltzmann equation for the energy of particles in heat is actually the energy on one direction, x or y, z, is actually half kT. It's actually proportional to the temperature. And anyways, I'm not gonna just bother you with that. This is physics. And basically that's it. So what's the main really properties? We're not going deep here. The main properties or the main application for this is that they play, these kind of diodes, they play an important role in gallium arsenide circuits. And gallium arsenide circuits, they are used mainly in fast switches actually, okay? They can be also used in rectifiers with high power applications. A rectifier that when you hear the word high power, that means high speed, okay? So if you have, like for example, high frequency rectifier, because the rectifier also, has a relationship with the frequency. So you need really fast rectifier, and for that matter, this diode can be used. Okay. Of course, in clamping as well and blah blah. But the main really feature, if you look at here in the graph, that's where I really need your attention here. Is that the regular PN junction is what you see in red. Okay. The Schottky barrier, what does it do basically? If you look at the blue, which is the characteristic or IV characteristic of the Schottky diode, is that the threshold here with Schottky diode is actually smaller than the barrier for the regular, meaning that the VD that is 0.7 with a regular diode, it becomes like 0.1 or 0.2, you know? That means the clamping or basically the rectification will start almost with the positive. It doesn't wait for the voltage to be above 0.7. So it's like almost ideal. It's not ideal yet, but close to ideal. Okay? And the same thing on the reverse bias. Here the knee voltage for this is actually a little bit smaller. So this is the main difference between the Schottky diode and the regular PN diode. Okay? Good. Let's keep moving. The varactors. Okay. The varactors, they are actually a type of diodes, and their names actually is composed of two words. Var means variable, and varactors, and this one, maybe actors only, is actually from the word capacitors. I don't know how they invented it. You ask the British people maybe. But when you combine these two words, you make this word varactor. So it's like a variable capacitor, which is good. What do you need really variable capacitor in your opinion? Huh? That's right. In tuning. That's it. To change what you call the resonance frequency. صح ولا لا? Make sense? You remember that? You need really something that you can change the L, you can change either L or C, I think, in that case. You don't want to change R, you want to minimize the power consumption, right? So you can change the capacitance or the inductance in the RLC circuit. So this guy can give you the opportunity to have a variable capacitor to tune your resonance circuit in tuning the radio, for example, receiver. So, to understand this, remember that when we analyze the diode, we found that, and by the way, this diode works only in reverse bias, not in forward bias. Why? Because the formula or the behavior of the capacitance there, we already discussed it. CG, the junction capacitance, is CG naught, a certain constant, divided by 1 plus VR, which is the reverse bias voltage, divided by V naught, which is the built-in voltage. Yes or no? Power M is the grading coefficient, which is a technology parameter. It's given by the manufacturer. And it shows how abrupt is the doping from N to P. Okay. We already discussed that. In any case, this is where, in red, where I want to take attention to. So to make CG, this capacitance, the junction capacitance, highly controllable by the reverse bias, what do we do? So what we do is basically to have the M, the grading parameter here, as high as 3 or 4. You said M in the abrupt approximation was what? Was half. The one that we studied was half. Yes or no? So now to make the voltage, the reverse voltage, has more control over CG, means if you plot this, if you use, for example, MATLAB or MathCAD or whatever, and try to change the R, you will not see the influence of the reverse bias voltage or the reverse voltage on the capacitance for lower M. You need to increase M to have the effect this visible on the capacitance. And that's what they did. Okay? So the manufacturer manufactures in a way to make M really high, as high as 4, if not higher. Okay? So this is the trick or technique to create factors. Okay. Very good. The application, frequency modulators. As you can see, it's all about communication here. Frequency multiplier in microwave receivers, RF phase shifter, and variable, this is what we discussed, resonant tank LC circuit. Okay? So, because I can control the capacitors. So this is the second type of diodes, basically. Okay? Now, what else? This one. This one is the one that we are using. The photodiodes is the one that we are using in this camera that we are using to shoot this video. So the photodiodes, they are diodes, but they are interacting with the light. And remember, the light does what in the semiconductor? It does. If you remember maybe the video as well, maybe you may or may not, but the light actually, when it comes, if it has enough energy, it can create electron-hole pairs. Now, once you create these carriers, there will be current. Do you understand? Now, if you create these electron-hole pairs, what happens? If you create them, especially in the detection region, and I'm teaching, by the way, a special course here, is actually introduction to cameras, introduction to CMOS image sensors, which is the special topic, ELEC315, which is an introduction to CMOS image sensors, which is the technical word for cameras. So we use and study photodiodes, which are in every single pixel of the camera, you find a photodiode, or a different type of photodetectors. So there is photodiodes, there is pinned diodes, and there is photogate. But the photodiodes are the first ones that have been used in making the cameras. Very useful. Okay, great. And to understand that much clearer, let's see the characteristic of what? Of the diodes themselves. So, first of all, this diode is actually a regular PN junction. So it's not special fabrication like a varactor. Okay? So it uses a regular PN junction. What else? It works in the reverse bias. That's the second condition. And it is interacting with the light. So it needs the light to come to it. So when the light falls, as I told you, a reverse current will try to, basically, which is proportional to the illumination, will try to, basically, at the beginning, we reverse bias it, and then let it go by itself, and this current will try to discharge the capacitors of this PN junction. Okay? For further details, you can send me email. I can send you some slides from this course. Anyways, but in any case, what I want you to look at is this. This is the IV characteristic. This is the IV characteristic of the diode under the influence of the light. So we said that diode is working in the reverse bias regime. It means at voltages that are negative. Now, if you put the diode like that there, and then you shine with the light, and you control the intensity of the light from dim, which is very low, to very bright, you see this. So at the beginning, when you don't have any light, you have what you call the dark current, which is nothing but almost IS. The one that we calculated it. Do you understand? That's it. Which is due to the minority carriers, yes or no? Now, as you increase the light, more minority carriers will be created, and the saturation current here will increase. More light. Here, what you see, the lux is the unit of the light intensity. So here's 1,000 lux, here 1,500, 2,000 lux, 2,500, etc. Okay? So as you increase the light, this reverse current will increase. Now, if you take this voltage as the operating voltage, and you try to take these nodes, the cross points here, and put them in a graph like this, where you have the illumination on this side and the current on this side, you take these and put them just in a different graph, you will find a very good linearity between the illumination and the current, which is excellent. We need linear behavior to understand, because why? The linear behavior, that means I have a linear relationship and I can easily understand, or it gives me a truthful image of the light, of the picture. So it's not making a picture fancy or something, it just gives me a copy of that picture in an electrical way. So from optical to an electrical. So that's the application of the photodiode. This is the symbol of the photodiode. So it's like a diode surrounded by a circle, and this is light coming to it. And the current, of course, because it's reverse, should be the other side, and that's the photocurrent. Excellent. So almost there, Almost there. The type of diodes is the LEDs. LEDs, they stand for light emitting diodes. And you can find them nowadays everywhere. From cars to this camera there, anywhere that emit the light, computers, this one, displays, etc. So LEDs are ubiquitous. Okay, ubiquitous. Okay, this is the word. Ubiquitous. I think I and tus. Ubiquitous يعني منتشرة. منتشرة بشكل كبير. So very widely used. Ubiquitous. Everywhere you find LEDs. Everywhere. From cell phone, I mean, you need a light everywhere. If you find a light source, most likely it's an LED. Now, how they work? So basically, the LEDs, they are basically a composite of three type of semiconductors. We have basically a P-type semiconductor and the N-type semiconductor, and between them there is what we call the active region. The active region is actually the region where the electron-hole pairs meet and they generate the light. Silicon does not generate the light. Why? I've told you before, maybe it was one of the questions, Bilal or somebody else, we said the band gap for silicon is indirect. So I don't want really to make you, but this is one of the reasons. Other semiconductors, they have band gap direct. You can dig that further, and then they can emit light. Silicon cannot because of that reason. So they put here an active semiconductor, I think, if I'm not mistaken, maybe germanium or some other semiconductors. They have really a direct band gap. Okay, good. So in the forward bias, okay, when the diode is forward biased, what happened? Holes from the P-type material and electrons from N-type material, they were, if you remember the diode, they were going opposite to each other, yes or no? Yes. Now they will meet. They will made here purposely to meet in the active so that they are combined. Once they are combined, boom, a photon comes out. Okay, you got it? Yes. They cannot in semiconductor, even if they meet in the semiconductor, they do actually, but they don't emit light because of the band gap. They don't have a very nice feature which inhibits them from emitting a light when they are combined. They actually emit heat. They make the silicon a little bit hot. That's it. So that's the basically the description of a very, very simplistic description of this diode. Again, this has to work where? In the forward bias. Okay? So, what is that? What is forward bias here? Here. So, each usage, each mode of biasing has its own merits and application. Okay? So, this is a very important. So, this is basically just a graphical description of what we said. And this is basically if you take an LED that you can buy from a store, small LED. So it has two poles, a P and N, okay? And there is a little mirror there. And inside that mirror, there is the semiconductor. Why we use the mirror is to focus the light, because the light that comes here, it goes this way, or that way, or that way, or that way. So you need to have what? A mirror around this, so to make the light go only in one direction. Got it? So it's like a micro mirror or small mirror, whatever you call it. That's it. So that's the light now comes on only one direction. That's it. So again here, without going deep, there is a linear relationship between what? Between the current that I put here in the circuit, and this is the symbol for the LED diode. It's again like for the diode, but the current is in the opposite direction. That's it. So, the more current you put, the brighter will be your LED. And there is a linear relationship. It doesn't continue linear forever, of course. There's a limited range there. But this is basically the major characteristic of this type of diodes. Now, if you take a cross-section of this, or if you use it in describing in data sheet, for example, they may include this or maybe this, but sometimes they may include this symbol, which is basically shows what is the anode and the cathode? So basically the anode is shorter leg and the long leg is actually the cathode. So when you buy it, you don't need to see plus or minus. The longer is the cathode and that's it. Got it?
Yes.
So when you buy it, next time maybe I'll try to bring some example. Just look at it. Which one is the leg longer? That's the cathode. Bingo. So you know how to use it. So in your circuit, you know which one is plus and minus. Put it forward and the LED will be bright. Okay, any question? If you have any question or suggestion or something, please don't stop. That's it. The rest is a summary for you. Okay, I'm not gonna read this. We covered all these things in this class. It was really a lot of fun. Okay, we really enjoyed it. I think, at least myself. Did you enjoy this chapter?
Yes.
You appreciate the application and usage of diodes? Yeah, diodes are really good ones. They do lots of stuff. So we need to have a good understanding of that to use them in our need, whether professional or even at home, if you want. Okay? So, any question? Okay, thank you very much, inshallah. I'll see you next week. And do not hesitate to contact me, email, phone, even personally. I have my office. Please come by and we should have yeah. Thank you very much.